हमें पता चलेगा यहाँ से तो फॉल्स आ रहा है, यहाँ से ट्रू आ रहा है, जिसका मतलब है दिस इज गोइंग टू बी ट्रू। तो जो चीज हमने लॉजिकली की उसी को हम अपने कोड में करने वाले हैं। यानी हमारा सबसे पहला स्टेप होगा कि जो भी हमारी सब रूट है, सब ट्री की जो रूट है, उसे हम फाइंड करने की कोशिश करेंगे इन द मेन ट्री। ये जो रूट है इसे हम अपने मेन ट्री के अंदर फाइंड करने की कोशिश करेंगे। और जहां पर भी हमें ये रूट मिल जाती है, जैसे फॉर एग्जांपल यहाँ पर हमें ये रूट मिल गई, उसके बाद हम चेक करेंगे कि ये पूरा का पूरा ट्री एंड यहाँ नीचे वाला पूरा का पूरा सब ट्री ये आइडेंटिकल है या नहीं है। इनको आइडेंटिकल चेक करने के लिए हम अपने लास्ट क्वेश्चन वाला लॉजिक यूज करेंगे, जिसमें हमने 2 ट्रीज आइडेंटिकल है या नहीं है उनको फिगर आउट करना सीखा था। तो आइडेंटिकल का लॉजिक तो हमें ऑलरेडी पता है, हमें सिंपली एक एक नोड पे जाना है, लेफ्ट सब ट्री आइडेंटिकल देखना है, राइट सब ट्री आइडेंटिकल देखना है और रूट की वैल्यू सेम है या नहीं वो देखना है। तो 2 स्टेप्स में हम अपनी प्रॉब्लम को सॉल्व करेंगे। सबसे पहले तो सब रूट को फाइंड करने की कोशिश करेंगे इनसाइड द मेन ट्री, और जैसे ही हम उसे फाइंड कर लेते हैं उसके बाद हम इज आइडेंटिकल चेक करेंगे फॉर हमारी सब रूट।
What if Google can see your site, but AI can't? SEMrush Site Audit checks both. Find SEO and AI search.
एंड मेन ट्री के अंदर जो हमें हमारा सब ट्री मिला है, ये दोनों ट्रीज आइडेंटिकल है या नहीं है। अब इसे कोड के अंदर कैसे करेंगे? हाउ डू वी एग्जैक्टली फाइंड वन सब रूट और वन नोड इनसाइड अनदर ट्री? ये तो बहुत सिंपल है। हम सिंपली जाएंगे और चेक करेंगे क्या ये वाली नोड इस वाली नोड के सेम है। फॉर एग्जाम्पल यहाँ पर भी 3 होता तो हमें पता चलता 3 और ये वाला 3 मैच कर रहे हैं। तो हम सिंपली क्या करते हैं, नीचे वाले ट्री के लिए चेक करते हैं ये और ये वाला ट्री आइडेंटिकल है क्या। अगर दोनों आइडेंटिकल हैं तो यहीं से हम ट्रू रिटर्न कर देंगे। अगर दोनों आइडेंटिकल नहीं है तो उसके बाद इसी 3 को हम अपने लेफ्ट सब ट्री के अंदर सर्च करेंगे एंड इसी 3 को हम अपने राइट सब ट्री के अंदर चेक करेंगे। जैसे एग्जाम्पल के लिए व्हाट वी आर एग्जैक्टली गोइंग टू डू, हम शुरुआत करेंगे इस रूट एंड इस सब रूट के साथ। हमें इस 3 वाली नोड को अपने ट्री के अंदर ढूंढना है, दैट इज द फर्स्ट स्टेप। हम सबसे पहले 1 और 3 को कंपेयर करेंगे, क्या ये दोनों सेम है? नहीं, ये दोनों सेम नहीं है। तो हम क्या करेंगे, 1 के लेफ्ट सब ट्री में जाएंगे। फिर हम 2 और 3 को कंपेयर करेंगे, क्या ये दोनों सेम है? नहीं, ये दोनों सेम नहीं है। नीचे और कोई सब ट्री एग्जिस्ट नहीं करता, तो अब हम 1 के राइट सब ट्री में जाएंगे। अब हम चेक करेंगे क्या ये 3 एंड ये 3 ये दोनों सेम है। यहाँ पर हमें दोनों सेम मिल गए। जैसे ही हमें सेम मिल गए, अब हमें इस ट्री एंड इस ट्री के लिए इज आइडेंटिकल को कॉल करना है। इज आइडेंटिकल चेक करेगा कि ये दोनों के दोनों ट्रीज मैच कर रहे हैं या नहीं कर रहे। अगर मैच कर रहे हैं तो यहाँ से हम ट्रू रिटर्न कर देंगे। अगर मैच नहीं कर रहे तो हम इस ट्री के अब नीचे की नोड्स में जाकर दोबारा से सेम इस 3 को सर्च करने की कोशिश करेंगे। क्यों सर्च करने की कोशिश करेंगे? क्योंकि हो सकता है यहाँ पर दिस वैल्यू कुड ऑल्सो बी 3 एंड दिस कुड बी 4 एंड दिस कुड बी 5। तो अगर हमने इसके लिए एंड इसके लिए चेक किया, ये तो हमें सेम नहीं मिले, तो हम क्या करेंगे, अब हम यहाँ पे जाके चेक करेंगे ये वाला 3 इस 3 से मैच करेगा एंड ये पूरा ट्री इस ट्री से मैच करेगा, तो उस केस में हमें ट्रू मिल जाएगा। तो कभी भी अगर इज आइडेंटिकल फॉल्स देना है तो हमें अपनी सर्च को रोकना नहीं है, हमें करते रहना है सर्च, क्योंकि कोई भी नोड हो सकती है इस पूरे ट्री की जो इसके साथ मैच कर जाए। तो इफ वी टॉक अबाउट इन टर्म्स ऑफ द रिकर्सिव फंक्शन, तो हमारे पास एक रिकर्सिव फंक्शन होगा, लेट अस कॉल दिस फंक्शन बूलियन इज सब ट्री। इस सब ट्री फंक्शन के अंदर एक तो हमारे पास हमारी रूट आएगी एंड एक हमारे पास हमारे दूसरे सब ट्री की सब रूट आने वाली है। अब सबसे पहले तो हम यही चेक करेंगे कि जिस नोड पर हम खड़े हैं, मतलब ये जो हमारी 1 वाली नोड है, इफ दिस नोड इज आइडेंटिकल विद दिस नोड, क्या ये 1 इस 3 के साथ मैच कर रहा है? तो सबसे पहली तो कंडीशन यही होगी। अगर ये दोनों मैच कर रहे हैं तो हम चेक करेंगे इनके ट्रीज भी आइडेंटिकल हैं क्या। मतलब अगर हमारी रूट की वैल्यू बिकम्स इक्वल टू हमारी सब रूट की वैल्यू एंड दोनों के दोनों आइडेंटिकल भी हो गए, मतलब अगर हम अपने इज आइडेंटिकल या इज सेम वाले फंक्शन को कॉल करें, लेट्स कॉल इट इज आइडेंटिकल फंक्शन को कॉल करें फॉर रूट एंड फॉर द सब रूट, तो उस केस में भी हमारे पास ट्रू आ गया। मतलब एक ऐसा ट्री है जिसमें यहाँ पे भी 3 है, यहाँ 4 है, यहाँ हमारे पास 5 है और दोनों के दोनों आइडेंटिकल हो गए, तो इसका मतलब तो हमें यहीं से ही ट्रू रिटर्न कर देना है। अगर ये दोनों कंडीशन हमें ट्रू रिटर्न कर देती हैं तो यहीं से ही हमें और कुछ चेक करने की जरूरत नहीं है, यहीं से ही हम ट्रू रिटर्न कर देंगे। अगर इन दोनों में से किसी ने भी फॉल्स रिटर्न किया, जैसे फॉर एग्जाम्पल 1 3 के इक्वल नहीं है, तो यही कंडीशन हमें फॉल्स दे देगी। फॉल्स दे दिया तो इसका मतलब है अब हमें लेफ्ट सब ट्री में जाके चेक करने की जरूरत है। तो हम क्या करेंगे, लेफ्ट सब ट्री की कॉल लगाएंगे पर उसमें सब रूट सेम पास करेंगे, क्योंकि हम ढूंढ तो इसी 3 को रहे हैं, इसके लेफ्ट सब ट्री को तो नहीं ढूंढ रहे, ढूंढ हम इसी की सब रूट को रहे हैं बट इसके लेफ्ट सब ट्री में ढूंढेंगे। विच बेसिकली मीन्स कि अब जो सब ट्री ढूंढने का काम है वो हमारा लेफ्ट सब ट्री करेगा या लेफ्ट चाइल्ड करेगा। तो हम इस सब ट्री को कॉल लगाएंगे सब रूट, फिर अपने राइट सब ट्री, दोनों राइट रिटर्न कर दी, तो हमें भी ट्रू रिटर्न करना है, जिसके लिए वी कैन यूज दिस और कंडीशन एंड यहीं से ही हम रिटर्न कर देंगे अपनी ट्रू वैल्यू को. सो दीज आर द बेसिक कंडीशन जिसके बेसिस पर हम चेक करते हैं इफ वन ट्री इज द सब ट्री ऑफ अनदर ट्री और नॉट. तो पहले तो हम उसी रूट के लिए चेक करते हैं, यहाँ के लिए इज आइडेंटिकल चेक कर दो, नहीं तो लेफ्ट सब ट्री हमें पूरा का पूरा काम करके दे देगा. लेफ्ट सब ट्री में आइडेंटिकल है या नहीं वो हमें चेक करने की जरूरत नहीं है, वो रिकर्सिवली अपने आप हो जाएगा. राइट सब ट्री में आइडेंटिकल है या नहीं है वो हमें चेक करने की जरूरत नहीं है, वो अपने आप रिकर्सिवली हो जाएगा. हमें तो सिर्फ अपने लेवल पे, रूट लेवल पे चीजें चेक करनी होती है. एंड रूट लेवल पे हम एक और चेक लगा सकते हैं नल वैल्यूज का इन द बेस केस. मतलब दोनों में से कोई भी, अगर एक भी नल हो गया और दूसरा नल नहीं है, इसका मतलब है वी आर नॉट गोइंग टू फाइंड द वैल्यूज एनीवेयर. तो यहां पर भी हम सेम बेस केस यूज कर सकते हैं कि कभी भी अगर हमें पता चलता है कि रूट या सब रूट में से एक भी वैल्यू नल हो गई, मतलब या तो रूट की वैल्यू बिकम्स इक्वल टू नल या फिर सब रूट की वैल्यू बिकम्स इक्वल टू नल, तो उस केस में हम रिटर्न करने वाले हैं रूट इक्वल टू सब रूट, क्योंकि दोनों के दोनों नल हैं. अगर ये हमारा एक ट्री है जिसके अंदर नल वैल्यू है, ये सेकंड ट्री है जिसके अंदर नल वैल्यू है, तो सब ट्री एक दूसरे के अंदर मिल ही जाएगा बिकॉज दे आर द सेम ट्रीज. उस केस में तो हमें ट्रू रिटर्न करना है. लेकिन यहाँ पर हमारे पास नल आ गया बट यहाँ पर हमारे पास कोई भी वैलिड वैल्यू है, या यहाँ कोई भी वैलिड वैल्यू है, यहाँ नल आ गया, उस केस में हमें फॉल्स रिटर्न करना है. सो दिस इज द सेम बेस केस जिसको हम अपने इस रिकर्सिव फंक्शन के अंदर लिख सकते हैं. इज आइडेंटिकल फंक्शन कैसे वर्क करता है उसको हम ऑलरेडी लिख चुके हैं, वही सेम कोड हमें बस कॉपी पेस्ट करना है यहाँ पे. एंड दिस इज द ओवरऑल लॉजिक जिसके बेसिस पर हम फाइंड आउट करते हैं इफ द ट्री इज सब ट्री ऑफ अनदर ट्री और नॉट. सो लेट अस कन्वर्ट दिस इंटायर लॉजिक इनटू द कोड. तो कोड के अंदर दिस इज द फंक्शन दैट वी वांट टू कंप्लीट. इस फंक्शन के अंदर वाली नोड नॉट नल है तो उस केस में हमें फॉल्स रिटर्न करना है, क्योंकि नल नोड कभी है लेकिन दोनों केसेस करती है, इसको हमें स्टेटमेंट मतलब दोनों में से टू क्यू, कोई भी एक अगर नल था तो उस केस में फॉल्स रिटर्न लिख दिया है, विच इज गोइंग टू बी द जिसके थ्रू हम चेक करेंगे इफ टू बाइनरी ट्रीज आर गोइंग टू बी आइडेंटिकल और नॉट। तो हम एक बार ड्राई रन भी करके देख सकते हैं। अगर यहाँ पर हम P पर खड़े हैं, यहाँ पर हम Q पर खड़े हैं, तो सबसे पहले हम चेक करेंगे P और Q में से कोई नल है क्या, कोई भी नल नहीं है, तो हम अपने लेफ्ट सब ट्री के लिए कॉल लगाएंगे। तो P के लेफ्ट सब ट्री एंड Q के लेफ्ट सब ट्री में हम
Today I want to go over another key search algorithm in graph theory, breadth first search or BFS. Suppose you were given a graph with the starting vertex and asked the question of finding the shortest path from that vertex to every other vertex in the graph. The BFS algorithm allows you to answer this question. In this video, we will go over the key intuition behind this algorithm, which will then lead us to an overview of the implementation of BFS. And in the last section of this video, we will go over a practical problem that shows one of the most interesting applications of BFS. Let's get started. Breadth first search is through the following analogy. Imagine a graph like this one represents balls with strings attached to them. Suppose you want to start a traversal of the graph from vertex 0. What you can do is imagine that you are pulling the ball that represents vertex 0 up until all the strings tighten. The shortest paths between vertex 0 and all other vertices are immediately clear, and the levels of the graph visually show a natural order for breadth first search, where we first visit vertex 0, visit all vertex 0's neighbors one by one, and then visit vertex 5. This was one of those visualizations that really helped the idea behind BFS click for me when I first learned this algorithm. Let's extend this intuition to a more complex graph. Starting at vertex 0, the idea of BFS search is that we are first going to visit a vertex and then visit all vertices of distance 1 from that vertex. After visiting all distance 1 vertices, we then continue with the natural progression and visit all distance 2 vertices. And this continues until we visit all vertices of the graph. Forcing an ordering where we visit all vertices closest in distance from that starting vertex is not only why the name of the algorithm makes sense, but also why it guarantees that the moment we visit a vertex, we have found the shortest path to that vertex. For example, the shortest path from vertex 0 to vertex 7 is discovered as soon as we visit vertex 7. As a result of this property for graphs with equal edge weights like this one, algorithms centered around breadth first search are the go-to method for solving shortest path problems. It's worth noting also that the order in which we visit vertices of the same distance from the start does not matter, so there are many valid BFS orderings. The BFS ordering shown here is one of those valid orders. Let's now take a look at the implementation for BFS. The BFS algorithm is quite similar to the iterative implementation of depth first search we went through in a previous video. We'll first initialize a Boolean list that will help us keep track of vertices we have already visited in our traversal. Initially, all vertices will have their respective marked value set to false. The key idea that is the core of BFS is that we will then use a queue to keep track of vertices that should be visited. While this queue is not empty, we will then remove a vertex from the front of the queue. If it hasn't been visited yet, we will visit the vertex, mark the vertex, and then iterate through all the neighbors and add any unmarked neighbors to the queue. To make sure this is clear, let's go through how the order is generated for this particular graph. Since we start at vertex 0, that's the first vertex into the queue, which is then promptly removed, visited, and marked. This vertex is the first vertex in the BFS order. We then add all of vertex 0's neighbors into the queue, where the order in which they are inserted does not matter. The next vertex we then pop off is vertex 1, since it is at the front of the queue. This vertex is then visited and marked, making it the second vertex in the BFS order. We then iterate through all vertex 1's neighbors, of which only vertex 3 is added since it's the only neighbor that is unmarked. We then go back into a loop and pop off vertex 3 from the front of the queue. This vertex has not been visited yet, so we again visit and mark the vertex. As a result, vertex 3 becomes the third vertex in the BFS order. Going through vertex 3's neighbors, we add 2 more vertices to the queue, vertex 2 and vertex 4. We then remove the next vertex off the queue, which happens to be vertex 2. You know the drill now, vertex 2 hasn't been visited, so we will visit the vertex and mark it, making it the 4th vertex in our BFS order. We iterate through all neighbors, but we don't add any of them to the queue since all neighbors have been visited. The next vertex that is removed from the queue is vertex 3, but this vertex has already been marked, so we move on. The same thing happens in the next iteration with vertex 2. We now have one remaining vertex in the queue, which is vertex 4. This vertex has not been visited before, so we visit and mark the vertex. This vertex is the final vertex in the BFS order, and after this point, the algorithm terminates since all of its neighbors have already been visited and the queue is now empty.
Politics and war is all about learning, networking, planning, and creating stories that will affect thousands of people for years.
Now that we've seen the implementation, let's take a look at a real-world problem. Suppose we were given an image represented by a grid of pixel values. Let's assume that these pixel values are just integers for simplicity. We are then given a starting pixel location as a row and a column in the grid and a new pixel value p. Our goal is to transform all pixels connected to the starting pixel to a new pixel value. Let's deconstruct what's going on here. Given the set of pixel values, you can imagine a corresponding image where the value 1 represents the color white and 0 represents black. This is quite an oversimplification, but it's one we'll make for now so that we can focus on the important parts of the problem. With this image representation, it's a lot easier to understand the notion of connectivity as it relates to an image. Connected pixels share the same pixel value and have a path between them by moving either left, right, up, or down. So, looking at an example, given a location of row 2 and column 2, our starting pixel is the center of this image. Our new pixel value is 3, and again for simplification, let's assume this is some new color like blue. The goal of this problem is to transform all pixels that are connected to the center pixel to this new color as shown here. Here's another example to further clarify. If we choose the starting pixel to be row 2 and column 4 with pixel value 5 representing the color yellow, this is what the transform image looks like. For those of you who have ever used a paint application like Microsoft Paint, this is essentially what the bucket tool does to fill a section of your painting or drawing with a new color. Let's now see if we can try solve this problem, which is often referred to as the flood fill problem. Describing this problem as transforming a bunch of connected pixels should be an immediate signal that this could really, underneath the hood, be a graph problem. Also, the fact that, this is a video about a graph algorithm, I suppose that could also be a bit of a giveaway. But in all seriousness, remember that connected pixels have the same value and are adjacent to each other in the left, right, upward, or downward direction. Suppose each pixel in this grid is represented by a vertex, and we take the idea of connected pixels literally and connect an edge between the two corresponding vertices. This is what the resulting graph looks like. And given the following input where we once again change the center pixel to a new pixel value, we can transform the pixels one by performing a breadth first search on the graph representation of the image. In fact, you could solve this with depth first search as well, either one works. I personally find the implementation using BFS a little bit more intuitive for this particular problem. Here's how we implement this solution. Our function takes an image, row, column, and a new pixel value. We first need to identify the starting pixel value since this will have a major impact on what pixels are connected to that pixel. And just like in standard BFS, we will initialize a queue with just the starting location as the first value in the queue. Since we will need to keep track of locations in the image we have already visited, let's keep track of visited pixel locations. After this, we follow the standard logic of BFS we just went through. While the queue is not empty, we remove the first element of the queue and mark it by adding it to the set of visited locations. We then transform the pixel from the old value to the new value. Then what we will do is take each row and column location from the neighbors of the current row and column location, and if that location has not been visited, we will add it to the queue. This is again following the standard BFS logic, and at the end we'll return the transformed image. The only thing we have to figure out now is how to implement this neighbors function. Here's a few examples of how we expect the neighbors function to work. On this image, the center pixel has the following 3 distinct neighbors, whereas the edge pixel has the following 2 neighbors. This function is going to be a little tricky to implement since handling of the edge cases in the very literal sense has to be carefully done. We can first start by defining the 4 possible directions explicitly. Then we need to check that each index is a valid index of the grid and the value of that index is equal to the starting pixel value, since that's one of our constraints for connectivity. Checking whether a pixel is valid is probably the most annoying part of this problem, but it can be done by making sure that both the row and column are non-negative, the row index is less than the total number of rows in the grid, and finally, that the column index is less than the number of columns in the grid. And it turns out that's really the final piece of the implementation to flood fill. This is a problem I've seen asked quite often in interviews, and people sometimes get tripped up because they don't realize that this is really just a graph problem in disguise. The biggest takeaway from this problem is that by looking at this problem from a graph algorithm perspective, it makes it so much easier and intuitive to implement. Sometimes the key to solving a challenging problem is just that clever shift in perspective. That's all for this video, and thanks for watching. If you
So you want to be a software engineer at Google? Go to algoexpert.io. Pick a question, read the prompt, write some code, run your code, write some more code, run your code again. Get stuck? Check.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve binary tree level order traversal. It's basically just like it sounds, so we're given a binary tree and we want to return the level order traversal of its nodes. So basically going through every single level of the tree and going from left to right. So for example, for this tree we have this level, so that's going to be one list. We have the second level, 9 and 20, and then we have the third level, 15 and 7. So we have 1, 2, 3 lists, and these lists are going to be put together, and that's going to be our result, the 3 lists in that order. So to understand what we want to do is pretty straightforward, right? So basically we have the first level, right? Go from left to right. We see that there's only a single node in this level, 3. That's going to be one list. We see the second level, right? That's what we want to do. We want to traverse this tree every single level, right? One level at a time, going from left to right. So the second level, we'll see 9 and 20, right? We want to add that to a separate list. And lastly, we'll get to the third level. Going from left to right, we have a 15 and then a 7. We're going to add that to the third list. And so we've traversed the list in level order traversal, and each of these sublists are going to be put together into a single list, and then that's going to be our result. So that's what we want to do. We know that that's pretty straightforward. So the only question now is, do you know an algorithm that can do that can traverse it level order? And if you don't, the algorithm is breadth first search. So we want to run breadth first search on our tree and then add the values into lists. And the second thing to notice is, do you know how to implement this breadth first search? So we need to know this is the algorithm to use, and now we need to know how to implement it, and let me show you how to do that. So we have a tree and we want to run a pretty standard algorithm on that tree called breadth first search. And you might know how to already implement this algorithm. You need a queue data structure because we're going to be inserting elements to the right, meaning we're going to, insert an element here, 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 right? We're going to be adding elements to the right portion, and we're going to be popping elements from the left portion. So so basically we're following first in, first out, right? The first element that gets inserted over here is going to be the first element that gets removed, right? So that's the order we're going to be doing things in. So the first thing we're going to do is take the first element, 3, and add it to our queue. This is basically to initialize the queue, right? And we know we're creating sublists, right? So what we're going to do now is see that, okay, count how many elements are in our queue initially, right? There's one element in our queue. So we're going to basically remove one element from our queue. We're going to see, okay, the 3 is in the queue. Now let's get rid of the 3 and add it to a sublist, right? Now the queue is empty. So we know that this sublist is complete. And what that tells us is basically we went through the entire first level, right? That's what we're trying to do. We're going through every level. We know that the first level only had one element in it, so now we're done. But when we pop that 3, we need to add its children, right? It has 2 children. It has a child 9 and a child 20. So we're going to add those children to our queue, and we're going to do it from left to right because that's important, right? We're doing this from left to right. So we're going to add a 9, then we're going to add a 20. Okay, so now we want to go through the second level of the tree, right? So we're going to have a sublist for the second level. Clearly, we have 2 elements in our queue. So we're going to basically pop these 2 elements from our queue from left to right. So the left is 9. We're going to pop 9 from the queue, add it to the sublist. So 9 is added to the sublist. And notice how 9 did not have any children, right? So we don't have to add any children for 9 into our queue. So next, remember we had 2 elements we were trying to remove. We have 2 elements in this level. So let's now pop 20 so we can add 20 to our sublist, right? So now clearly this level is complete. We added both nodes in the order 9 and 20 to a sublist. But notice 20 had a couple children. It had 15 and 7. So as we remove 20 from our queue, we're adding its children to the queue for the next level, right? Because we know we want to keep going down a level. So when we get here, the values will already be added to our queue.
This is Valorant. Aren't you tired of playing FPSs where teamwork is non-existent?
So 15 and 7 are added to our queue. We're done with the second level. Now time to go to the third level. We see that there's 2 nodes, 2 values in our queue. So we're going to pop both of these values. First, we pop 15, add it to the sublist for the third level. And then we pop 7, add it to the sublist for the third level. Neither of these nodes had any children, so now we're done. We know we're done because our queue is now empty, right? There's nothing left in our queue. So we created a sublist for every single level, and as the question wanted us to do, we're going to package all 3 of these sublists into one list and then return that as our result. So we're really just doing a breadth first search algorithm with a queue on this binary search tree. And since we're doing it like that, the time complexity is going to be O of n. We're only visiting every single node a single time. The memory complexity is also O of n because our queue at any given point in time, our queue could have up to n divided by 2 elements in it because the biggest level of a tree could be n divided by 2. That's how trees work, binary trees at least. And so we know that n divided by 2 can be rounded to big O of n. So the memory complexity is big O of n with breadth first search. So with that being said, let's jump into the code. So first, let's initialize an array for the result. And we also, remember, want to have a queue. So in Python, we can do that with collections.dec. this will give us a queue, and the first value we want to initialize this queue with is the root node that we're given. So with that, we can start running the breadth first search, and we're going to run breadth first search while our queue is non-empty, remember? And since the queue is non-empty, we're going to get the length of the queue, right? So we're going to get the number of nodes or values that are in this queue currently, and we're going to loop through every single one of those values. This queue length is basically ensuring that we iterate through one level at a time. We're going through one level at a time. And with those nodes from that level, we're going to be adding them to its own list, right? And then we're going to add that list to the result list. So I'm going to loop through every value in this queue currently. So for queue length, I'm going to pop nodes from the left of the queue, right? First in, first out. And it's technically possible that the node could be null. So I'm going to have a check to make sure it's not null. Then we're going to take the node value and append it to the list level. And don't forget, this is also important that to our queue, we make sure to add the children of this node. So node.left and node.right. Technically, these could be null, but that's why we have this if statement. So then when the next loop comes around, right, we come around to the next iteration of the while loop, it'll make sure to check that these nodes are non-null before adding them to its own level list. Okay, so now we have the loop in place that's going to iterate through every node of a single level. After we've done that entire level, what we're going to do is take our result and make sure we add every single level to that result, right? And then we're going to keep running this outside while loop, the outer while loop, until there are no nodes left in our queue. That's how we know we've gone through every single level, added it to the result, and then at the end we can finally return the result. And one last thing we want to do is make sure that if we're adding a level to the result, we want to make sure that level is non-empty. Because we know technically our queue could have null nodes. We're not adding null nodes to the level list, so we want to make sure that level is non-empty if we're adding it to the result. We can run the code and see that it does work, and it is pretty efficient. This is a breadth first search level order traversal of a binary tree. And we did it in linear time.